Hi all. Today we're going to continue on with our topic 1 on equilibrium systems. So this is the second part of the lesson where we're going to learn how to actually carry out calculations involving chemical equilibrium. So whenever we're dealing with equilibrium-based problems, to undergo and actually go through to figure it out, we're going to use a strategy that uses an ICE table. Where ICE is an acronym, where I stands for the initial concentration of our reactants and products before the reaction has actually taken place. C stands for change in concentration of our reactants and products. Okay, so it's going to show us how much our concentration of both the reactants and products will change to establish an equilibrium. And E stands for our equilibrium concentrations of the reactants and products. We're going to see how we can use these ICE tables, similar to basic stoichiometry problems that we've seen in grade 11, to go and actually calculate the equilibrium concentrations for reactants and products. So in here, just to keep in mind that in this table, the only values that are going to go in there are molar concentrations. So the units are going to be moles per liter. Okay, so unlike our stoichiometry-based problems where we included moles or mass or molar mass, the only thing that will go in an ICE table is the molar concentration. So to see how to use an ICE table, let's try to work through a sample problem. So in here for sample problem 1, it says HF is used in the production of many important substances, such as medicine. It can be synthesized from H2 and F2. And we have this balanced equation where we have one H2 reacting with one F2 to make 2 HF. So the question says, when a chemist starts with this chemical reaction in a sealed container at SATP, meaning standard ambient temperature and pressure, the initial concentration of both hydrogen and fluorine gas is 2.00 moles per liter. And there's no HF initially present. We're asked to solve for the equilibrium concentration of H2 and HF, and we're told that the equilibrium concentration of F2 is 0.48 moles per liter. Okay, so let's try to break down what we're given in the problem. So we know our initial concentration of H2 and F2. They're both 2 moles per liter. We're told that we have 0 HF, so that concentration is 0 moles per liter. And we know at equilibrium that the concentration of F2 is 0.48 moles per liter. We're going to talk about this equilibrium concentration for F2 later, once we've actually set up our ICE table. And ultimately, what we're trying to solve for is the equilibrium concentrations for H2 and HF. Okay, so to do this, like we said, we're going to try to set up an ICE table. So now we're going to try to walk through how to actually do that. So to set up an ICE table, we're going to go through and basically set up the same idea like we did with stoichiometry, where we're writing out our balanced equation. Okay, so here we have our H2, F2, and 2HF. Okay, and then we're setting this up into kind of 2 parts. Here's where we're writing out our ICE on the bottom. So we have ICE, where our I stands for our initial molar concentration of the substances. Okay, C stands for our change in concentration, and E stands for the equilibrium concentration. Okay, from here, we can go through and write in the information that we are given in the question. Okay, so we know that we are starting off with 2 moles per liter H2, and that we're starting off with 2 moles per liter F2 and 0 moles per liter HF. I would like to see you write in the units here. I apologize that I didn't include it for this one. For the change and the equilibrium, you don't need to include it, but just as kind of a general workflow, we will include the concentration here. And I have a full sample problem at the end of this that shows you exactly what I would expect for you guys to plug in. Okay, so we're setting this up just like we did with the stoichiometry-based problem, where we have our balanced equation, and this is setting up a table where under H2 we're putting all the information that we know for H2, we're putting all the information that we know for F2 underneath F2, and all the information for HF. Okay, and we started off with writing out what we know the initial concentrations were, and we were provided this in the question that we have 2 moles per liter H2, 2 moles per liter F2, and 0 moles per liter HF. Now, for part 2, what we need to start trying to do is write our change in concentration. Okay, so looking at this, we're starting off with 2 moles of H2 and F2 to start off with. So the only direction that this reaction can go is to start to form products. Okay, so that means that the concentration of H2 and F2 is going to decrease, and the concentration of HF is going to increase. So we're going to choose a variable to indicate this change, okay, because it's going to change proportionally based on the coefficients in our balanced equation. Okay, so for us, we're going to go through and choose a variable, and that variable is going to be x. Okay, so the concentration of H2 is going to change by minus x. Okay, so minus some variable in moles per liter. Okay, and that it's minus 1x because the coefficient in front of H2 is 1. If we're looking at F2, its concentration is also going to change by minus 1x because the coefficient in front is 1. Now, when we're looking at the products, their concentrations are going to increase. So it's going to be a positive change that's occurring. And because the coefficient in front of HF is 2, it's going to increase by 2x. And the writing here just goes through to try to explain that in a little bit more detail. Okay. Now we have one more section to fill in, and that's our equilibrium concentration. Okay. So in here, what we're going to do is to solve for the equilibrium concentration, it's simply going to be your initial concentration added to your change in concentration. Okay. So we're going to have 2 plus minus x, which is simply going to be 2 minus x for our concentration of H2 at equilibrium. For F2, it's going to be the same. So it's going to be 2 plus negative x, which works out to be 2.00 minus x. And HF is just simply going to be 0 plus 2x, which will just be 2x. Okay. So now that we have it set up, we have our ice table. Now we can go through to try to solve for the equilibrium concentrations. And in the question, we're given some really important information. So based on our ice table, we know that the concentration of F2 at equilibrium is equal to 2 minus x. We are told in the question that the concentration of F2 at equilibrium is equal to 0.48 moles per liter. So now we know that the concentration of F2 is equal to 2 minus x, and it is also equal to 0.48 moles per liter. So we can set these two equal to each other. So we can say 2 minus x is equal to 0.48. And then we can solve for x. And if we do that, we're just simply moving these around. Okay, so we're moving the 0.48 over. So it's 2 minus 0.48, and then x is coming over here. And now we get a positive value of 1.52. So from this, now we know that the change, our x in this table, is equal to 1.52. So using this information, we can solve for the equilibrium concentrations for each of the other substances in this question. So we know that the concentration of H2 at equilibrium is 2 minus x, and we know that from our ice table over here. So now we just need to plug in our value for x, which we found to be 1.52. So we're taking 2 minus 1.52, and we get an equilibrium concentration of H2 of 0.48 moles per liter. And we can do the exact same thing for HF. We know at equilibrium, the concentration of HF is 2x. So I can plug in my value for x, which was 1.52. So the concentration of HF at equilibrium is 2 times 1.52, which is 3.04 moles per liter. And now we've gone through and you've used your first ice table to solve the problem. Okay. Now over here, this just shows a little bit more simplified view of the calculation and what I'd expect to see from you guys going through. Okay. So you can see here we have our balanced equation. I set up my ice table, ICE, plugged in the initial concentrations, 2.00 moles per liter for H2, 2.00 moles per liter for F2, and 0 moles per liter for HF. Notice how I included the molar concentration, which I didn't do on the last one. The change in concentration for H2 and F2 are both minus X because the coefficient in front of the equation is only 1, and it's going to change proportionally based on that. The concentration of HF is going to change by positive 2X. It's going to increase because it's produced during the reaction. So we can go through and write out our equilibrium expression being 2 minus X for both H2 and F2. We're simply adding these two together, and HF is going to be 2X. We know the concentration of F2 at equilibrium is 0.48 moles per liter, which is also equal to 2 minus X, which we got from the ice table. If we set them equal to each other, we can solve for the value for X, which is 1.52, and then solve for the respective equilibrium concentrations for H2 and HF. So what you see here is what I would expect to see from you guys for a equilibrium problem. Let's try one more sample problem. So in sample problem 2, it says when NH3 is heated, it decomposes to form N2 and H2. A chemist adds 4 moles of NH3 to a 2.0 liter sealed rigid container and heats it. And then the figure below shows the change in the amount of NH3 observed over time. Okay, so here we see our moles and we see our time. The balanced equation for this reaction is 2NH3 yields N2 and 3H2. And we want to solve for the equilibrium concentrations of N2 and H2. Okay, so I have two versions. So this is the version of the answer that goes through and shows my solution. And I'll go through that. If you want to go through and see a little bit more where it's written out, if you keep following through the next set of slides, I have a detailed breakdown of the problem. So in here, we're told in the question that we have initially 4 moles of NH3 and that the volume of the container is 2 liters. So in our ice table, we only include molar concentration. So I need to solve for the initial concentration of NH3. And we know that concentration is equal to moles divided by our volume, so N divided by V. Remember that volume always needs to be in liters for molar concentration. So we're taking 4.0 moles and dividing it by 2 liters. So our initial concentration of NH3 is 2.0 moles per liter. So we're setting up our ice table. So we have 2NH3 undergoes an equilibrium reaction to yield N2 and 3H2. We're writing out I, C, and E, where I stands for our initial concentration. Initially, we have 2 moles per liter of NH3, and we have none of our products. So 0 moles per liter of N2 and 0 moles per liter of H2. The concentration of NH3 is going to change by minus 2x because the coefficient here is 2. And the only direction this reaction can shift is to the products, so the concentration of our reactant must decrease. N2 is going, our products are going to increase. N2 is going to increase by positive x, and H2 is going to increase by positive 3x because the coefficient is 3. So for our equilibrium concentrations, we're simply adding our initial and our change. So we're taking 2.0 minus 2x for our equilibrium concentration of NH3. N2 is going to be 0 plus x, which is simply x. Our equilibrium concentration for H2 is going to be 0 plus 3x, which is simply 3x. Now, to solve for the equilibrium concentrations, we were given a graph here, which will allow us to solve for our moles of NH3 at equilibrium. Looking at this, we know when equilibrium is established, once this graph stabilizes. Okay, so we can see here where I've drawn this red line, this is where our equilibrium has formed. And we can see that at equilibrium, we have 2 moles of NH3, which I wrote down over here. Okay, so our moles of NH3 at equilibrium, as determined based on the graph, is 2 moles per liter. Because we always need to deal with molar concentrations when we're dealing with ice tables, we need to convert this into a molar concentration. So I'm dividing our moles that we got by our volume, which was 2 liters. So we get a molar concentration of NH3 at equilibrium of 1.0 moles per liter. So now we know that the concentration of NH3 at equilibrium is equal to 2 minus 2x, and it's also equal to 1 mole per liter. So we can set these two equal to each other. So we can say 2 minus 2x is equal to 1, and then we can rearrange to solve for x. And we find that our value for x is 0.5 moles per liter. From there, we can use this value for x and plug it into our ice table to solve for our equilibrium concentrations for N2 and H2. So we know the concentration of N2 at equilibrium is equal to x, so that's simply 0.5 moles per liter. The concentration of H2 at equilibrium is 3x, as we can see from our ice table. So we're taking 3 times 0.5, and we get 1.5 moles per liter. So now using our ice table, we found the equilibrium concentrations for both N2 and H2. Okay. That basically concludes the second part of this lesson, and you'll find in class we'll go through and spend some time trying to practice carrying out these reactions, these calculations.